First of all, I want to thank Don and all of LFCS for an invitation to come. It's really a great honor and has always been an honor to visit all of you. And in fact, I've been visiting for 25 years, so I'm calling this Visiting LFCS over the past 25 years. So, and I hope, in fact, I'll be here again in the fall, so I hope to see many of you in the fall. That will be my last sabbatical, so I think that will be time to say goodbye there. But, so it's been a great honor and privilege to visit LFCS over many years. And I really appreciate, of course, both the kindness and collegiality of many of my colleagues here. The first time I visited was in 91, 92. And my memories of that were the following. We were out in King's Buildings, and I remember constantly being lost. I could never figure out how to get from one office to the next. And I always ended up back at George Clellan's office, and the secretary would kindly show me where I was. The other thing I remember was it had terrific barbecues for visitors and grad students, and we would all meet outside and look at the hills, and it was wonderful. And maybe the key thing was that there was extraordinary researchers who were there. There was staff, there were grad students, postdocs, visitors, in a huge range of areas of study, and people were doing both practical things and pure mathematics. It was just quite amazing to me as a visitor from out in the hinterlands in Canada. So I was quite impressed by this. The first thing that we did when we were a visitor here was there was a room with all the yellow and green covered preprints. So everybody would run like crazy there. And I remember Prakash told me, you have to go in there and just grab as many as you can. So I went in, and I still have many of those that were referred to today. It was great. And I think these preprints, in many ways, gave to the world a view of the foundations of computer science as a discipline, a way of looking at things which was extremely important and foundational and radical at the time. I still have very engineering-oriented colleagues in computer science in various departments, like my own university, who are still pre-LFCS in their view of what computer science is. So there's no doubt that this LFCS has created modern computer science in many ways, or at least the Euro theory part, as Mark Jerram would say. There was a curious tradition, though, which that year I was there, we tried to breach. And that was, there were both the LFCS and math departments were in the same building. And one was higher up and one was at the bottom. And they were totally disjoint. There was never a history of them ever meeting. And so I was visiting. There was also another visitor, Phil Mulray, who was visiting at the time. And we decided to try, I tried particularly to do something about it. So, and I remember Gordon said, well, see what you can do. And so I went and talked to a friend of mine who happened to be there, Angus McIntyre. And I said, why don't you come and talk in lab lunch? And he came, and then we had a little conference at that time on sheaf theory and things. And Mike, I remember, spoke on topos theory, and several of us spoke on toposes, and some of the mathematicians came, and they were very impressed by hearing some of the category theorists speaking from LFCS. And it was actually, it went well, although I think after we left, it went back to the old, the way it was. But at the time, it was very, very nice. The grad students, now I'm going to ask for apologies for those who are here and whose names I didn't mention. These are just the ones I remember and that I had dealings with at the time and have now, in the case of many of them, written papers with. But I remember certainly Torsten Altenkirch and Marcello Fiori and Philippa and Neil Ghani and Martin Hoffman and John Longley and Eugenia Moji and David Pym and Davida Sangiorgi and Alex as this very well-known, well, now well-known computer scientists who were all amazingly graduate students during the while I was there. And you can't imagine anywhere else that you could have had such talent in such a small concentrated group of graduate students. Amazing. I should also say that, representing Canada here, that we sent over 2 Australian-Canadian category theorists to you, Barry J. and John Power. Barry J. was, they both finished, I think, the same year, roughly the same year at McGill. And I don't know if John came directly over at that point, but Barry was a colleague of mine for a year at Ottawa, and then he said he would like to go here as well, so we encouraged him. And so you inherited both of our, at that time, newest students. It was, and what was happening is that LFCS, in my mind, had become a major center for developing and applying category theory, both in the foundations of mathematics as well as in the foundations of computing. Now, of course, things change, and I don't know if it will continue, if that's an area of interest that will continue, but certainly for 25 years or more, it's been the center. And for many category theorists, I think LFCS became one of the centers of category theory along with Montreal and Sydney. Of course, now, in the case of Montreal, everybody is gone, but Sydney is still booming and as a center, and there's still a lot going on here in Edinburgh. So I think that that's a great legacy there. In fact, you can see a lot of it in the history of LFCS. I mean, Rod Burstall, who I have over the years enjoyed very much speaking with and getting to know, with Joe Gogan, did some early work which is still going strong on institutions. And then Mike Foreman came from being a category theorist into computer science. Gordon, of course, and his many students and collaborators and postdocs all used category theory. And then when Sampson came here, he brought, again, yet more students and postdocs in and his own categorical methods. So that LFCS has a great tradition of category theory in its scientific methodology. What I did the first year, I thought I would briefly mention. It's something that is not something I've followed up too much, but it was something that was kind of interesting to me because it gave an opportunity to meet with a person here. When I first came, I met Robin Milner. And Robin was very enthusiastically telling me about this new invention of his, which he said is called pi calculus. And so, oh, what's that? And he was explaining it to me. And there was a postdoc here, Gianluigi Bellin, who perhaps was Gordon's postdoc, I don't know. Anyway, Gianluigi Bellin and I started talking to Robin, and we thought, oh, well, gee, maybe we could translate linear logic proofs into pi calculus, see what they look like. And we started to do a bit of work on that, and then that year, Sampson came and visited from Imperial, and he gave an important talk called Proofs as Processes. And he gave a very general program of how one might try to represent various fragments of linear logic, starting with the multiplicatives and the additives and the exponentials, how one might try to do this in a process calculus. And Robin was very kind, and he kindly gave us a version that he called synchronous pi calculus, especially for our work. And he said, here, try this. You'll find this might be very useful. So we worked away and worked away and worked away at it. And it led eventually to a kind of a long paper called Pi Calculus of Linear Logic, and an introductory paper by Sampson in the same volume explaining the whole proofs as processes viewpoint and his program that he wanted to do. And it was quite an interesting phenomenon. And in there, I'll just mention briefly, I don't want to talk about, I'll try to keep Don's advice and not to be too technical, but I'll just mention that there was the idea of information flow and the idea of having a sound and a local full translation for the different levels, multiplicative, additive, and the full exponential linear logic, and seeing how information flow in proof nets related to the pi calculus reductions. We were never able, one of the things we were trying to do is Robin would come running in one day and say, I have these fantastic way of translating evaluation of a lambda expression into pi calculus. And you do this, send this, and you do this, and do this. And we could never figure out what he was. And he would explain it and explain it over and over, and we couldn't get the intuition. So for us, at least, what happened was we just wrote it as a sort of a typed proof, and then we took the translation, and lo and behold, out popped out Robin's translation. So we call it the Milner translation. Then there was a separate one for Sampson translation. And it was in that way kind of satisfying for us, but I would say as a logician, it wasn't really very satisfying, the whole project, because it turned out that pi calculus is essentially alogical, that it would support, it really had nothing to do with logic, except for the most trivial level, multiplicative linear logic, where you get lockstep simulation. Beyond that, you would have to make the rewriting of pi calculus coincide with cut elimination. In the logic, you had to put in various constraints. You had to put in guarding. You had to put in equations and all kinds of things. And so eventually, it was sort of a hack. And it was interesting that it could be done, but it really wasn't conceptually what I had hoped for. But it was interesting, and you'll read, if you actually look at the paper, there's lots of discussion about ending up with garbage terms and garbage collection, and there was all kind of interesting things that helped us learn a lot about linear logic, in which Sampson already probably knew, I think, at the time. But so anyway, that was sitting in the background. And then 2 years ago, I was here visiting, and I happened to walk on the second floor of informatics, along there, and I came across Jacques Fleurio's office, and he had this great big poster. And it was about work that he'd been doing on formal modeling and verification for healthcare in hospitals. And curiously enough, he had been using exactly this formalism of our paper. And I was really excited to talk with him, he and his student, Mr. P there. And that was great. But then I noticed there was he had kindly put my, or I thought he had kindly put my name on the poster, Phil Scott. And then I found out, as we now know, that there are two Phil Scotts, and there's another one who's actually a student here. So it wasn't me, but it was nevertheless very interesting. And I don't know if he's continuing that project, but for a couple of years, he really had this interesting healthcare formal verification project based on this proofs of processes idea. I should mention here, I wish I knew how to get rid of this thing. Does anybody know? Oh, click that, the X. Ah, that didn't work. What happened?
Maybe just move the pointer away from you.
Ah, okay. So let me try slideshow again. Thank you. So I should mention that in this particular Robin's synchronous pi calculus, if anyone's actually interested in it, the idea was that the prefixes, you were allowed to permute them, provided nothing bound became free and free became bound. But other than that, you were allowed freely to permute the prefixes. If you're interested in that, Frank von Bruegel wrote a very interesting kind of monograph, which he never published, on the rewriting theory of that kind of synchronous pi calculus. And it's been looked at by Moravsky and Lukong. And I think probably for those who want to go farther into it and what perhaps should have been done, at that time, Robin hadn't yet developed a proper bisimulation approach to the theory. So a student of Vincent Danos, Emmanuel Bifara, has looked at similar things using bisimulation on pi calculus. So that would probably be a better way of doing proofs of processes if you were interested in that. So then, all right, so then there was a period of time where I visited LFCS, but not for very long, and or I was coming through. And what happened was I came again in 2000. And this was when Sampson, I believe, was already here. Is that right, Sampson? Yeah. And there were various ideas surrounding linear logic that were being developed by many people at the same time. And the two themes that here I'm mainly going to talk about, in fact, all of my things are just what has influenced me, because Don had asked what is this how has this affected my work? So these are two things that influenced me at that visit. The first was I'd been working on an implicit computational complexity a paper with Girard and Shedroff on a system of linear logic called bounded linear logic, which exactly captures p-time. And so then I came here, and there was Martin Hoffman, who I think must have graduated by then, so I guess he was teaching here. And there was a postdoc, Patrick Bayot. And they were both working in implicit computational complexity. Martin was finishing up his habilitation on complexity theory. And so he said, we really have to figure out how bounded linear logic fits into all this. And we wrote a paper which, to me, was a really a fantastic experience, because it was a new way of looking at this older work that we had previously done using proof nets and geometry of interaction and all kind of techniques. And this was a completely different way of looking at it. And it's called realizability models for BLL-like languages. And there we introduced some kind of p-time BCK algebras, which I think have now been developed. I know, I believe Samson has looked at such things. And now I should mention Robin Cockett has developed a whole theory, categorical theory of complexity, based on kind of realizability-like models. And meanwhile, this community, Martin Hoffman and Bayot and so on, have developed the ICC into a large community, but this is kind of in some ways a byproduct of their stay here at LFCS. I think it was a major developing ground for that. The other area that I worked in for a long time, and still in many ways do, is things that Samson mentioned, full completeness theorems. Well, I don't work in game semantics, but these were topics that were in the air at LFCS at that time, probably under some of the influence of Samson. And Gordon was also working in this. Game semantics, geometry of interaction, and traced monoidal categories. I've lectured on these things a lot, so here especially, and so I won't talk about that, but I thought I would mention two theorems which predate LFCS, very old theorems, which I think are extremely influential. Were influential, I know, for me, but I think they were influential on Gordon, and they were certainly influential on that era of semantics. And the two theorems are the following. One is called Leuchli's theorem, the other is Harvey-Friedman's theorem. Now, Leuchli's theorem is an interesting theorem. It's about you're trying to model provability in intuitionistic logic. I'll just state the one for propositional. He also had predicate. And he proved that a formula of intuitionist propositional logic is provable if and only if, whenever you interpret the base types as Z sets, those are sets with a permutation on them. So that's an interesting topos. If you interpret the base types as sets with a permutation on them, then the interpretation of a formula, so it's if and only if it's provable, if and only if its interpretation has an invariant element. This is kind of like a generalized proof, a global element. And so this was quite an important thing. It led to a lot of early work in logical relations and other ideas. It explicitly is the theorem that led Lorvier. He mentions it specifically as one of the inspirations for his development of topos theory. And this theorem has really been a very influential thing. And I know Gordon mentions it in one of his papers early on. The second one is kind of a theorem that anybody who thinks about lambda calculus must have just assumed. And it's the following, that whenever you have type lambda terms, you say, oh, these are just functions. So in what sense are type lambda terms really just functions? Well, they are. So it turns out that Friedman proved that if you take the full set theoretic model of your type structure, but if you let the base types be interpreted as infinite sets, then two lambda terms are beta eta equal if and only if they're the same function. Yeah, it's quite an amazing thing. And so lambda calculus acts like it's supposed to act, set theoretically. So these two theorems had a lot of enormous influence. For example, Friedman's paper is not so well known. If you go and look at it, pers were first introduced there in Friedman's paper. These, I think, influenced a lot of the early work at LFCS. But the thing that I wanted to talk about briefly, the thing that I've spent a lot of time doing, and for a while, was full completeness theorems. Now, this terminology and some of the viewpoint here is due to Sampson, I think, or it's certainly terminology. And it arose in his early work in game semantics and his work in trying to understand what is the Milner-Plotkin idea of what is full abstraction. So given a typed logic L, or if you want to look at it as some kind of a free category, that's fine. We're going to say a model. So here by model, I mean not a model of the logic, but a model for the proofs. So we want to have proofs now. So we say a model category is fully complete if for some interpretation of the base types, you get a unique interpretation of the logic into the model, and we demand that that thing be surjective, or full, if you like, as a functor. And it'd be even nicer if it's faithful as well. And so what that says is that to be full or surjective just says that if you have a map in the model between definable types, it comes from a proof. And if it's faithful, it comes from a unique proof. Well, that's kind of neat. Every definable map comes from a proof. So what happened was that the first such examples of this came from Sampson's work in game semantics, and he wrote a paper on this full completeness theorem with Radha Jagadisan and JSL. And this was really the beginning of a kind of a subject. There was a period of time of 3 or 4 years there where every LIX had at least 1 or 2 papers of full completeness, and somebody proved it. And Gordon had one, for example. I don't know if I mentioned. Anyway, he has a domain theoretic. Plotkin and Von Pratt and so on had a proof of full completeness for a fragment of linear logic using domains. And Sampson and Martin Hyland and Ong and all the collaborators had various fragments of linear logic, again, full completeness using a structure like this, where it's a model of games. Rick Bluth and I decided no games. We wanted real kind of standard traditional mathematical structures, so we had topological vector spaces. And then there are other models, geometry of interaction models. And so this became an interesting project. I should mention here, though, that there was a main caveat. The caveat is that the model had to arise by magic. That was a key fact. In other words, the model you have to be a surprise. The theorem is boring if the model is close to the syntax. I mean, why don't you just take the identity function? That's full and faithful, no problem. Now, the point is the models should have on the face it have nothing to do with syntax. Vector space is something. And then you prove the theorem, and whoa, it actually is syntax in its secret guise. So anyway, that was the main tricky point of these kind of theorems. They were very interesting, and as I said, they were really popular during that period of time. Another topic, I'm not going to go into geometry of interaction with you, but I will talk a little bit, just briefly, about traced monoidal categories. Because, first of all, both Sampson and Gordon have spoke about them many times. I've even seen Gordon give a wonderful talk on them in applications in biology. So it's an idea, it's an algebraic formulation of feedback. So given a map from X tensor U to Y tensor U, you want to get a map from X to Y by just feeding back to U. And so it's an operation. It's a family of operations which takes maps of this shape into maps of this shape, or proofs or programs of this shape with inputs and outputs of that shape into programs with inputs and outputs of that shape. And the idea is that this notion should be somewhat like a homomorphism. So it should be natural in this variable, natural in this variable, natural in those two in the appropriate sense, called dinatural. It should you should ask what is, it should be a homomorphism. You should say, well, the trace of F tensor G should be something like the trace of F tensor trace of G. And trace of the identity should be something like, so the idea is that it should be something like a homomorphism. What happens when U is of the form U1 tensor U2? Then you get the trace of a trace, you get the so-called Beckich property. So you can write down the equations. It's very nice. It's a natural notion. And there are many, many examples of this trace. What happened was, for me at least, a major fundamental influential thing happened from somebody from LFCS, namely Gordon, but not here. There was an MFPS meeting in Montreal in 2003. And Gordon gave a fabulous talk, which he's never written up, on how to define partial traces. So you assume that process of tracing here is not always well defined, but some class of maps, the domain of this thing, will be the maps which are called trace class. And those are kind of interesting, and it led to a whole theory of what these partially traced categories would look like. The partial traces are much trickier to write down, and in fact, at the time, I think Gordon hadn't yet completely decided what the traces he was interested in were, or what equations were, but you had to write conditional, so all the equations that you would write down in the category theory language were conditional equations. If such and such is defined, then. So it was all clean inequalities and implications, and it was very messy to work with for those who've done higher recursion theory. It's a messy kind of system of equations. It turned out they were axiomatized by a student of mine, S. von Hagverdi and myself, and we worked on this for a while. And eventually, we were able to prove a theorem with a student, characterized with a student of myself and Peter Selinger named Octavio Malherbe, and more recently, a student of Girard Bagnol, Marc Bagnol, who's my postdoc now, has given a new proof of this result, but it's a complete characterization of these kind of partial traces. And so the idea of these partial traces is that you have a subcategory, you have a submonoidal category of a big category. And I want to know when you have a partial trace on this subcategory. And it turns out to be, it's exactly when it's a monoidal subcategory. So that's kind of a cool thing. And of course, Gordon would ask I was talking to Gordon a couple days ago, and he said, yes, well, what happens when you look at it at complete metric spaces? What's this ambient category? And the answer is we don't know. I mean, it's a pure free construction, but I don't know in concrete examples what it looks like. And so we're still not there yet, and Gordon and I still hope to someday be able to come back and talk about this with respect to, say, analog computing. That's what one hopes. But so these partial traces are important. I remember another member, no longer here, of Vincent Denos in biology, got very excited with these partial traced categories and said this is exactly what they were looking for solving systems of local equations, partially defined equations. And he also asked what this ambient category is, and we don't know in any of it. So those are all open questions. I should mention, by the way, am I through? I'm through. Okay, so let me not. I'll just mention then one or two slides of very brief. I visited LFCS a bunch of times, as I said. One time in 2010, I had I call it an honor, I suppose, of being the Flock workshop chair here. And it's hard to say no to Moshe Vardy, of course. And Leonid Lipkin and I worked like crazy for Flock, but it was an extreme pleasure, actually. I really enjoyed working with the staff here at Informatics, and we had a great time, but we wouldn't really want to do it again, I think. But what I'm doing now, and so on my next time coming here, I'm going to be talking about a new topic. I've mentioned it to a few of you. I've given some talks here on it. I've become interested in fuzzy logic, so logic of Lukashevitz logic and MV algebras, and the work of Daniela Mundici, who's a logician in Florence. And Mundici connected up MV algebras with a program in AFC star algebras, these are algebras which arise in functional analysis and in quantum work. And in quantum physics, they're related to another area called effect algebras, which are partial algebras, a little bit like MV algebras. And this is an area that's been developed heavily by Bart Jacobs, some of you know, in Nijmegen. So I guess those are the things that I'm now working in, and so I hope to be able to talk to some of you about that and its connections with computer science. So again, I want to thank, it's been a great honor and pleasure, and hopefully continuing to be able to come here and visit you and talk with all of you on these topics. Thank you.